Okay, so this is going to be a continuation of last week's talk where we talked about the basics of fiber bundles, and I specifically tried to emphasize like structure groups as like a topic to aim for, structure groups and principal bundles. So today we're going to talk about how these things fit into the picture of homotopy theory. So in order to talk about homotopy theory, I'm going to have to introduce this stuff in the first section. And then we're going to talk about something very special that fiber bundles have called the homotopy lifting property, which is going to be very powerful and powerful enough to make us define a new class of objects to be objects that just satisfy this property. And then from there, we're going to discuss the phenomenon of universal bundles, which are sort of a particular bundle over a particular space that essentially represent any other bundle. So any bundle over a space X can be given as the pullback, which we'll talk about today, of some of the universal bundle over some classifying map. And the homotopy class of that classifying map distinguish it from other isomorphism classes of bundles over X. So there's going to be a correspondence here between homotopy classes of maps from X to the classifying space and isomorphism classes of principal G bundles over X. So that's going to be the main thing that I want to hit, because that's super, super important. And our main example for vector bundles are going to be these classical Grassmannian manifolds of like D planes in R infinity. And so I'm going to give like a construction for this topologically, and kind of, I forgot to come up with a justification for why they are classifying spaces, but it's okay. And then if time allows, we're going to revisit all of that stuff about structure groups and reductions of structure groups from the perspective of homotopy theory, and so that you can actually come up with sort of algebraic quantitative obstructions for certain lifts of classifying maps, or being able to tell that a bundle is not orientable, for example. So that's the recipe for today. So let's jump right into section 1. So the first word in the title is a homotopy, so I'm going to define what is a homotopy. So there's two definitions I'm making here. One is a plane homotopy, and other is a pointed homotopy. So a pointed space is just a pair of X and a point in X. So this is the typical data of a pointed space. It's just a point with a choice of base point. And a homotopy, I like to think of a homotopy, it's a function defined on X times the interval. So that's a cylinder, right? So let's say this is X cross 1, X cross 0. And when we map this into Y, basically it looks like a sequence of movies of slices of X. Maybe they shrink, maybe they grow, maybe they twist and turn, maybe they spin around or something. It's basically just a movie of images of X inside of our codomain. And yeah, I guess the word continuous deformation could be used synonymously with a homotopy. That's the main idea. For a pointed homotopy, we have the additional condition that the base point of X, supposing like this is the base point of X, we have the entire line corresponding to that base point, so this is the base point cross I. That entire thing is supposed to get placed at one point. So this particular homotopy that I drew is not a pointed homotopy because it's moving the point around. But I could draw a different picture that maybe looks less crazy at this point. So a pointed homotopy might look something like this. So you have one circle here. Here's the base point. Base point's supposed to stay there forever. Maybe you have a family of circles like this, something like that, where you have one circle image and you're sort of sweeping it over to this other circle image while keeping this point fixed for all time. So that'll come into focus when we're talking about homotopy groups, but this is just our definition. And if you have two functions from X to Y, this allows you to define a relation between them. We say that they're homotopic, or we denote it like this, if there's some homotopy that starts at F and ends at G. So right, this function from the X into Y is homotopic to this function from X into Y. It is pointed homotopic. Okay, so that's just a basic definition. while we're here, we're going to make a follow-up definition. Just because I'll probably say it a lot by accident, so if you don't have the definition, it's not very helpful. So x and y are homotopy equivalent. If. So here we require, so typically in topology, two things are isomorphic if they're homeomorphic. If you can establish a bijection between them that's continuous in both directions. So instead of just requiring that both compositions be equal to the identity, we weaken this by just asking that they're homotopic to the identity. So we say that they're homotopy equivalent if there's a pair of functions. Let's start with f, g, y to x, continuous, so that if you do g and then f, or f then g, then this is homotopic to the identity of x. And if you do f and then g, sorry, other way around, this should be homotopic to the identity of y. So like I said before, if you replace these homotopy symbols with equal signs, you just recover the definition of a homeomorphism. So this is sort of like a slight weakening, kind of like wobbly version of a homeomorphism. It doesn't say that these things are like rigidly the same, but it says that they're more or less the same. So here's sort of the classical example. Let x be circle, say in R2. Y is the annulus, which is, I'm going to take minus 1/2, sorry, just 1/2 to 3 halves. We'll do the math for a second there. And so here's our x. Y is 2 circles, is the unit circle. And our one inclusion, so the inclusion function from x, this x onto this circle, is going to be one of our functions. And the other function is going to be normalization. So this is going to send something in this annulus to the normalization of it on the unit circle. So you can go and check that this is indeed a homotopy equivalence. One of the compositions actually is equal to the identity, but the other composition takes all of y and maps it back down to the unit circle. But then you can just sort of continuously descale that operation and define a homotopy yourself by hand. But yeah, last time I did a lot of gritty work, getting my hands dirty, working out specific examples, and this time I'm not going to be so hands-on, and I'm going to leave more to the reader. And so that's a good exercise to actually make sure that you know what a homotopy equivalence is. And you call this pair, so FG, well, either one, F or G, is a homotopy equivalence. And you could also say that G is a homotopy inverse of F. And since you have this wobbly homotopy instead of equal sign, a homotopy inverse isn't unique in the same way as like an inverse function is unique. But I'm pretty sure, you know, I forget, I think I did convince myself that a homotopy inverse is at least unique up to homotopy. There's a unique homotopy class of homotopy inverses. And this is an equivalence relation, and we call the equivalence classes homotopy classes of functions. I forgot to give that notation, so I'm going to make that really interesting. Or do I want to do that on a new board? I think I'll actually just do that on a new board and not overload it. Okay. So this is some notation, I guess, rather than a definition. For spaces x and y, well, let's say pointed spaces, let's do a double definition again. And yeah, homotopic, you can also upgrade that to pointed homotopic just by requiring a pointed homotopy. So for pointed spaces, x, y, and the base point is just going to be, you know what the base point is supposed to look like. We denote closed bracket x, y, close bracket. This is the set of all continuous functions from x to y, modulo the relation of homotopy. So this is the set of homotopy classes of functions, continuous functions. And, or for pointed, basically the same notation, but I'm going to put a little bullet sign there. And so this is all pointed continuous functions, x, y, modulo pointed homotopy. That's just some useful notation. Okay. Does anyone have any questions that they want to ask at this point?
I have one.
Yes.
So for functions, you have a function, I guess that enough? Okay. So is there a, like without having to go down to homotopies, if I just give you an f, is there a way to know whether it induces a homotopy equivalence? Or do I need to, like, is that not a trivial, like, or I guess not trivial in general, but like, is it incredibly hard just from giving you an f? If you, I know.
It can be. So like by definition, the way to see something's a homotopy equivalence is by constructing a homotopy inverse.
Yeah.
Something that's really close to a homotopy equivalence, and that, like, I haven't used this language yet, when we define homotopy groups, a continuous function induces homomorphisms on homotopy groups, and a homotopy equivalence will induce isomorphisms in every degree. And so if you have a function that induces isomorphisms in every degree, we call that a weak homotopy equivalence. For the category of CW complexes, those are also homotopy equivalences. But there are examples of something that induces isomorphism on homotopy groups, but is not a homotopy equivalence. And here's an example, and this is often called the Warsaw circle. You start with gamma equals graph of sine of 1 over x for x in, let's say it's between 0 and, why not, 2 pi or something like that. Probably going to draw it wrong, but you just need some closed endpoint. And then, so what does this look like, right? You've got your 2 pi, you've got your 0, comes in like this, and then it starts oscillating faster and faster and faster, and it doesn't really have like a limit point here. But if we take the union, let's call it j. Let's say this is the vertical bar at 0. So what is that going to be? X is 0 cross, and then it's going to be minus 1 to 1. Ooh, I could have used color here. So let's say j is green. J is for green. So we add our green bar here. So this construction so far is called the topologist sine curve. It's an example of a space that's connected but not path connected. And so if you take this, I don't want to lose these, and you include one more piece that goes from the green bar to the tail of your graph here. So So what do we call this thing? Let's call it W equals gamma union J union whatever this red line is that is not worth it to give an actual definition for. So if we take this thing, this is called the Warsaw circle. So then all of the homotopy groups of this Warsaw circle are actually 0, but the Warsaw circle is not homotopy equivalent to a point. So this is a space which is weakly contractible, but not contractible. So I think that was too long of an answer for your question. I think that does answer your question. Yeah, so it is hard to tell if something is a homotopy equivalence, and you can typically use homotopy invariance to test whether it's not a homotopy equivalence. But for CW complexes, you can get away with finding out that it's a homotopy equivalence by checking it on homotopy groups. Okay, good question. Okay, so I'm going to get to the next part then. That was a good start. Where would I like to go? Do the cardinal sin and erase my plan talk here. It's recorded, it's fine. Okay, so I think that's the next topic already. So homotopy lifting property. So, how do I say, okay, I have something that I can, so definition. So let's just start with a continuous function, say, from things we'll suggestively call E and B. Okay, so the homotopy lifting property says, if you have a homotopy downstairs coming from some space X, you have a homotopy in B. If you choose an initial condition of a map from X up into E, then there is an extension of that initial condition which covers the homotopy. I'll also show you what I mean by that. So F has the homotopy lifting property. I'm going to say for all X, and you can choose your favorite category of X to some extent. So for all X and homotopies from X cross I into B, how do I say this? How about given a map G from X to E such that, first of all, it has to cover the initial part of X in B. So here's our homotopy at time 0 in B. And then upstairs, we've chosen some lift of this initial map into E. So this is the setup. For any situation like this, there is an extension of G to G, a homotopy, a full-on homotopy in E, so that it covers the original homotopy in a way that I make specific in this diagram. So here's our F, here's our full homotopy H, and then we have G. And so, let's see, yeah. This is the homotopy lifting property. And so this commutes. And so we would say that G is a lift of H. Okay, so essentially, if this map F has the homotopy lifting property, if whenever you have a movie downstairs and you choose like a first frame upstairs that's compatible with your first frame downstairs, you can produce a movie upstairs which is compatible with your entire movie downstairs for all time. It's a really esoteric property, but it has a lot of really deep consequences. Oh no, I forgot to do something. Have I forgotten to do something yet? Yeah, I'm doing this out of order. It's okay. It's okay. So this is the homotopy lifting property for bundles, and the result is that bundles have this property. So I'll write this, I guess, right here. I meant to define homotopy groups in this initial homotopy theory section, but now that I'm already talking about this, it would be too confusing to bounce back to that. So I'm going to have to just reorganize on the fly, I guess. So, theorem. Bundles have the homotopy lifting property. And moreover, covering spaces. So these you can think of them this way because they are this. A covering space is a fiber bundle whose fiber is discrete. So covering spaces, so these are bundles with discrete fiber have unique homotopy lifting property. Meaning that the G that you're supposed to get, which is a lift of H, once you've chosen this initial condition, your G is actually uniquely determined for the case of fiber bundles. So I'm going to illustrate this with the drawing, sorry, for covering spaces. So for example, here's kind of how it works. So we've got your thing downstairs, right? So our bundles, fiber bundles, the whole idea is that you can find local trivializations. So suppose we have this local chart U, and we've trivialized our bundle over that. So if we have a discrete fiber, that means the fiber over this U, our trivialized fiber, is just going to look like U times some discrete space. So it's just going to have this classical like stack of pancakes picture. So if here you have like your X, then you have a number of points living over X in the fiber. So at least in terms of a path, so a path is a very special type of homotopy, I just erased it, where X is a singleton space. So let's consider the case of actually you're trying to lift a path. And suppose you have a path going through your point X or whatever. Suppose you've already lifted it up until this point. Then whatever fiber, then because these fibers are disjoint, the part of the path that you've already lifted has to live entirely like within one of them, as long as you're being careful enough about making your neighborhood small enough. Which means that to continue the homotopy lift, you have to start in this fiber where you've already lifted your path. And because it turns out that the projection map restricted to each of these slices is actually a homeomorphism onto this part, these are all identical copies of U, your hand is forced. There's only one way that you could possibly follow this path downstairs through this fiber upstairs. So this is where the uniqueness of homotopy lifting property comes from for covering spaces. Because the fiber direction is trivial, you have all you can do is follow what's happening downstairs. The only thing you have to figure out is which component of the fiber it's happening in. If you had a more general fiber bundle, the idea is that like you could go up or down or whatever, so your lift is not unique in that case. Nevertheless, you do get some lift. And a lot of the times, the different lifts, I think I did figure out one time that the lifts are all homotopic over H. I think that is true. But it's important to be aware that you just get some lift, but in covering spaces, it's actually unique. That does come into play sometimes. Okay. So, what's the best possible thing to do next? Yeah, so now let's talk about consequences of the homotopy lifting property. I'll do that by defining one of our major basic constructions that I should have talked about last time, but I forgot, which is a pullback of bundles. The idea is that suppose you already have a bundle over your space Y, and you have some space X, and you'd like to put a bundle on X. If you have a map from X to Y, any continuous function, you can just decide that the fiber over any point in X should just be the fiber over the point in Y that we map it to. You have to be careful about doing that because you might have two points in X going to the same point in Y. So the way you circumvent any collision problem is just to label the fibers with the points in X that you're mapping it to. So this is encompassed really nicely in the definition of a pullback. So let's see, let B, and let's say that we actually have a fiber type F specified. Let this be a fiber bundle. We're not concerned with structure groups for this definition at all. It just has fiber F. Let X, say F to B be continuous. then the pullback of E along F is defined rigorously as follows. So notationally, we put an F upper star and then E, just to be consistent with things like pulling back differential forms and stuff like that. This is going to be the set of pairs. One of the elements is going to be in the base space, or the space X that we want to put fibers over. The other element is going to be in our total space E. And like I said, over any particular point, we want the fiber of the map to just be the fiber that lives over f of x. And so we can cut out a subspace of this big product by just saying that f of x, well, put it the other way, how about pi of E is f of x? So saying that E is in the fiber over x is precisely this statement. So this is the condition that cuts out the pullback bundle from this big product. Like I said, when you unravel this definition, that's all you're doing. You're just taking the fibers over B in E, and you're labeling them with elements of X, just to avoid these collision problems. And this is a fiber bundle with fiber F. So the projection to X just takes this pair X comma E to little x, and like I said, the set of all E that live over this one particular point, well, that's a copy of F, because that's just the fiber over F of X. So this is, yeah, and is a bundle fiber F. There is, one thing I could say about structure groups, if we want to be concerned about them. So if you have a trivialization of the bundle over B and then pull back the bundle, by taking the inverse image of all of these open sets, you're also going to set yourself up with a trivialization of your bundle over X. And in fact, the transition functions, if they were chosen to be in the structure group G over B, the pullback transition functions are also going to just naturally find themselves in G. So if you're also imposing a structure group, so I'll put this here in writing. So G bundles, they pull back to G bundles. So once we start talking about classification of principal bundles, that's going to be important. Okay, so I'm almost at the consequence that I'd like to point out. So in particular, taking a bunch of the definitions I've set up so far, here's something we can just do. So let's let, this is going to be a proposition. Should be a theorem, I guess. I don't know the difference. So let's let E to B be a bundle. And let's let H be a homotopy from X to B. So then we can pull back the entire bundle H star E to X cross I. Right? So this is a bundle living over X cross I. And we have two possible restrictions. We can do, let's see, what's the right way of saying this? Yeah, sure, I'll say it like this. So we have an entire bundle over X cross I. So the theorem is that if X is paracompact, or maybe if it's B is paracompact, either way it's true. One of these nice spaces. Then the two ends of this bundle that we pulled back are actually isomorphic. So H0 star, pull back of E along H0, is actually isomorphic to H1 star of E. So this is called homotopy invariance. It's really important. Here's an immediate corollary. Let's box this off. X is contractible and sufficiently nice, like paracompact, then any bundle X, any bundle over X is trivial. So why is this a corollary? Well, we can just choose a homotopy equivalence of X with a point, right? We can just, being contractible means you can take the identity function of X and shrink it down to a point. So that entire homotopy from X cross I, so what you can do is pull back whatever bundle you have over X. So let's take the contraction homotopy and pull it back. Let's say maybe it's called kappa, and you have a kappa star E over X cross I. And there's also, I forgot to mention, you also get a natural map to E. You can project to the X coordinate, you can also project to the E coordinate. Both of those are perfectly good morphisms, but the X coordinate actually gives you a fiber bundle, whereas the E coordinate is just something else. It's a bundle map over X. Right, so if you have this contraction homotopy, right, you get that kappa star, so kappa 0 star of E is the identity star of E, which is E. And then kappa 1 star of E, this is the constant function, pull back E, and this is just the fiber over whatever is your constant point, say X naught, contracting onto X naught, across the rest of X. Yeah. So that's the idea. Yeah. So this is kind of how you use homotopy invariance, is you start plugging in really, really important homotopies, like a contraction homotopy. Look at what happens on both ends. See that on one end, in this case, we had the identity function, so you just get E back. On the other end, we have this contracting down to a point. So the pullback of the constant function, right, everything has the same fiber. So it's just the trivial bundle. Okay. So that's good. Does anyone have questions they'd like to ask about that? Can we switch to another topic right now?
I have a quick question. If you don't remember, it's fine. For the proposition, are you saying that just with X paracompact, that's enough?
Yeah, this is one of these statements that's not true for like every space.
Okay. What I'm trying to say is, like, doesn't matter with B, if B's paracompact or not.
Yeah, I mean, I think the result is that the whatever pullback, the H star of E has to be a numerable bundle.
Okay.
It's one of those things. So like if B is paracompact, then E is paracompact to be, but like B could be really crappy, E could be terrible, but if X is paracompact, it's going to be
I see.
There's like lots of assumptions you could put in to make it work.
Okay.
It's kind of hard to like juggle what's the best one. And in like all of our cases, everything is paracompact. Like we never have to worry about it really.
Okay, so we need the result for manifolds where you get like paracompactness easily. But,
That's just, I believe, from second countability. Yeah.
but like, so that's why like for manifolds, like it's easy.
Oh.
But I didn't know where you needed the.
Oh yeah.
It's easy.
Yeah. You have to have like a good cover, basically. Yeah, for like smooth manifolds, I think you can prove this with like some vector field stuff, like some floats things. But like, yeah. Whole point of topology is that you can't do that. Okay. So, like I hinted at, now I'm actually going to talk about homotopy groups because that's where we're going to see the next huge application of the homotopy lifting property. And I really should have done this in the homotopy theory section. Okay, so let X, that's not, be a pointed space. And choose a base point for the n sphere, say. Let's say the first basis vector because this lives in every sphere. So it's a consistent choice we can make. Then nth homotopy group. This is just, you take all pointed maps from the sphere into X, and then take pointed homotopy classes. And we usually specify the base point in the case that X is not path connected, it makes a difference. But often we drop it when it's clear what the base point is, or when it's clear that the base point doesn't matter. But for the definition, it's in there. So we're going to take all pointed maps like this. Okay, so you've probably seen the example of the first homotopy group, which is a fundamental group, and the circle. But on the other hand, I can't assume that you have, because these are classical topology things. But I'm going to plow ahead as if you have. Okay, so this is what we're going to call it the nth homotopy group. So I'm going to list some properties. So one is that this is a group. As long as n is actually positive. Turns out, so there's no natural group structure you can put on it when n is 0. But when n is positive, you can. And here's my picture of how to do it. So suppose you have f and g mapped from the n sphere to x in such a way that it sends base point to base point. Then what you can do is take your big n sphere and say, like, there's your E1. And you can do a clever pinch map. You can take this entire equatorial sphere and crunch it down so that what you get is 2 n spheres glued together at one common point. And when you form this quotient map, this point contains this base point that we already had. So this is a new point. Okay. So I think that concludes the homotopy crash course portion. And now I'm going to get back to how we're talking about bundles, okay? Yeah, I'll go here. I always prepare way too much.
How does the circle act, or like on S infinity?
Which one?
Like in the first example for CP infinity?
Oh, that's just because S infinity lives inside, in that S infinity I'm imagining it's living inside infinite complex space.
Yeah.
And so S1 is just the unit scalars.
Okay. So you just
using the vector space structure.
And in that one you're thinking about it as living in like H infinity.
Yeah.
And then you act unit quaternions on it.
Yeah, S3 being unit quaternions in that case.
Okay.
Yeah, for sure. And then you can try to do the same with octonions, and it doesn't work.
Okay.
There is no OP infinity, unfortunately.
Sad.
There's an OP2. That's as far as you get, though. You get stuck. Okay, so here's a huge black box. So back to classifying bundles. I think we're at like part 3 or something. Here's a black box. No intention of trying to explain this. Okay. Suppose G, topological group. Suppose you have a bundle called EG over a space called BG. Principal G bundle. And suppose that EG, total space, is contractible. So these are both, assume that we have these two things. So then for any principal G bundle over any nice enough space, X is nice, there exists a classifying map C from X to BG bundle that you started with is isomorphic to the pullback of the strange contractible bundle under the contractible total space. And moreover, to be even more specific, if we say prin G of X is the isomorphism classes of principal G bundles over X, this is in bijective correspondence with our homotopy classes of maps from X to BG. And what is the correspondence? You take a homotopy class F and you just take it to the pullback of E. So this is a case of a universal object. So EG is called the universal principal G bundle. BG we call the classifying space. And I said I should have said a classifying space, but the fact is that BG is unique up to homotopy equivalence. And seeing that is actually not hard. You just apply the universality condition. Being a universal object kind of makes you unique up to isomorphism, because you can just kind of classify your own universal object, and that has to be classified by the identity map. Okay, so for example, there's some classifying spaces up there. I just made some. Right? So because this is contractible in all three of these cases, right, I presented this to you in some homotopy theory thing, but these are actually classifying spaces as well. So CP infinity is the classifying space for S1, which we also like to call U1. RP infinity is the classifying space for S0, which we also like to call O1. And we also like to enjoy calling this V mod 2 whenever it's convenient. HP infinity being the classifying space for BS3, which I think is, how do you call this? SP1? SP1?
Yeah.
Yeah, okay. Yeah. Symplectic transformation. So we already have classifying spaces. And, yes, we already did one above. The circle is the classifying space for the integers. That's cute. So any map to the circle gives you a principal integer bundle. That's fun. Okay, and sure. Is anyone confused about the statements before I go into? In fact, I have to actually think about how much I should be doing for the rest of the talk. So I at least need to say that classifying spaces exist as well. So this is the theorem of Milner that I need to communicate to you, but I won't really do a lot of justification. I'll just refer you to Wikipedia or something. Milner's infinite join. So the theorem is that for G, any topological group, this bundle exists. There is a universal bundle. And the way that Milner does it is by the infinite join construction. So e.g., you define, well, it's a topological operation called join, which I'll let you look up on Wikipedia. I don't really have time to get into it. You join a bunch of G's together. The more you join spaces together, the more highly connected they get. So it's a theorem that this thing is actually contractible. And BG, you can have G acting on each of these factors. And this is diagonal action. BG is just the quotient. Turns out that this construction is good enough that this quotient gives you a vector bundle. This being contractible means that this is a universal bundle for the group G. So this is just to, I'm not expecting you to understand this, I just wanted to show that, well not show, but tell you that universal bundles do exist.
And this can happen in, in a finite number of joins, or
No, that's infinite, yeah.
it's infinite in general?
Yeah. Oh,
Okay.
yeah. To make this contractible, you have to join infinitely many G's together. Unless your group G already was contractible, in which case the classifying space is also contractible.
Mm-hmm.
So you don't actually have to do it.
Okay, yeah.
So now I want to focus on, yeah, okay. Due to time, I think I'll just cut to the chase and give the example for higher orthogonal and unitary groups, but I won't do the full construction of it and justify stuff about group actions and things. So we've got a speed add-on here. What do I say? Okay, so this is what we're going to do. Let S T K R K plus N equals the Stiefel manifold of K frames. So as a set, we think about this as a tuple of vectors. Yeah, an ordered tuple of vectors where each of them lives inside R K plus N, and it has to be orthonormal. There is an appropriate topology that you can put on this, and I just don't have time to really talk about it very much. There is a
Is this just a subspace topology?
No, it's a quotient topology. All right. You take the orthogonal group K plus N, and you take the quotient by the lower. Yeah, I'll take an identity of size K here, and then block sum with OK. So, yeah, the idea is that this group, this really big group, acts on this set, and if you pick a particular base point, the stabilizer subgroup is going to be something that looks like this. So if you take, for example, the first K, this should be an N. If you take, for example, the first K basis element, standard basis element as your base point of this set, then the stabilizer subgroup of that base point is this subgroup.
I'm pretty sure you get a subspace topology anyways.
Subspace topology of like
the a big R to the K plus N to the K. Because you can look at it as acting, right? You can look at K plus N acting on R K plus N times K, then the stabilizer is going to be I plus R, so you can just quotient out. I think you do get the subspace topology.
Yeah, I've never thought about it. Never tried to find it as a subspace topology. But that would make sense because you want them to vary as elements of this set would vary. So yeah, maybe it is just the subspace topology. Sure. Easy enough to describe. Oh well. So this is our Stiefel manifold of K-frames. So since we're already talking about actions, we can talk about how OK also acts on this space, Stiefel manifold. Given a K-frame, that induces for you automatically a isomorphism between the subspace that they span and RK. And then using that induced isomorphism, you can just have an orthogonal element acting on subspace that they span. It's sort of built in for you automatically. So OK acts on the Stiefel manifold, and the orbit of any particular K-frame, well, you're just making all possible K-frames inside of that subspace that it spans. So what you're essentially just recovering is the subspace itself. So there's a quotient by this, something called GRK, RK plus N. This is the Grassmannian manifold. By the way, these are manifolds. None of K planes. So your Stiefel manifold is composed of frames. Your base space Grassmannian manifold is composed of just the planes. And there's another black box that I'll have to just make you go look up. STK. I'm going to say something stupid like this, not really specify what I need. But as you let the n go to infinity, these spaces become higher and higher connected, so that if you consider the Stiefel manifold of K-frames in R infinity, this actually becomes contractible. So this is the fact that if you take this colimit, this becomes contractible. You still get a quotient map to the Grassmannian K-planes in R infinity. This is a universal OK bondle. So this is the usual model of the universal OK bondle, is the Grassmannian. And it makes sense from an intuitive point of view as well, because you imagine if you have something that you can manage to embed into, I'll say it like this instead. R infinity is big enough so that if you think about the space of all K-planes in R infinity, this is a suitable model, at least for a category of nice spaces. This is a suitable model for the universe of K-planes. So that when you're mapping into this space, every point that you map into this space is picking out a K-plane. Well, by pulling back, by just saying, okay, my fiber over the point is going to be that K-plane, maps to this just naturally give you K-plane bundles. But the other part of the story, the contractibility of this, that's what ensures you that any K-plane bundle over any sufficiently nice space has a classifying map into this Grassmannian. So one really concrete example would be if you have a smooth manifold and you're trying to classify its tangent bundle. Whitney embedding theorem says that any smooth manifold can be embedded into a sufficiently large Euclidean space. Once you have this embedding, now you have these concrete tangent planes that exist at every point. So the tangent bundle is classified basically directly by that embedding by just saying, okay, the tangent plane is literally this K-plane in R infinity. So constructing representatives for classifying maps for tangent bundles on manifolds is actually straightforward, assuming you know how to construct embeddings into R infinity. And then the real code, and I'll just mention that analogously this stuff works in the complex case as well. Well, in many other cases. So B of UN, like the Grassmannian of N planes in C infinity, where these are complex planes. We can also talk about BSON, which is maybe not analogous, but this still works. So BSON has a model of Grassmannians of N planes in R infinity with the additional structure of having an orientation assigned. So you can construct it like we did up there. So the GR, let's think about the construction. So in terms of constructing our space out of actions, we could have done this. So this space we also could have constructed as SO n plus k modulo SO k cross SO n. So the difference between these, this is actually really interesting. If you take an orthogonal group like OK plus n and mod out by On, since like this has elements that are in both of the connected components of this quotient is actually the same as SON modulo, or SON plus K modulo SON. So in fact, like the Stiefel manifolds are the same because like orientations come down to basically ordering of frames anyway. But then to make the unordered Grassmannian, you're quotienting out by twice as much. Right? This group is twice as big as this one. So in fact, there's a natural map from BSON to BON, which is forget your orientation, and this has a Z mod 2 fiber. So this Z mod 2 corresponds to there being two choices of orientation on every bundle, or sorry, on every vector space.
You can always do that. If you have like a subgroup H of a group G, you always get like induced maps between BH and BG.
Yeah, so I didn't say anywhere, but it is true, that B is functor. B is a functor from topological groups to spaces. And I think you can even set it up so it's a functor to pointed spaces. So like if phi from G to H is a homomorphism, then yeah, this gives us an induced continuous map B phi from BG to BH. And so now that you've brought that up, I might, considering what time it is, well, so I wanted to talk about the relationship between lifting structure groups, changing structure groups and lifting classifying maps. So it's like 7:30 now-ish in a few minutes, so maybe I don't want to talk longer than 2 hours. So I'm not going to really like expound on it, but I want to at least say it because that was actually the secret goal of this whole talk, is to relate structure groups to these classifying space constructions to turn these reduction problems into a quantifiable algebraic problem. So I'd like to do this.
Can I ask you a question? So if I know, for example, in the case of BUN and BSON, this Z mod 2 fiber, I can think of it as the fact that I have to connect the components, or like the like, I guess, can I say it like, okay, what I'm trying to say is, if I know what G mod H is, do I have information about the fibers of this map?
Yeah, so definitely don't have time to talk about this, but there's a result that says that this is a fiber sequence.
Okay.
Meaning that any three of these are like homotopy equivalent to a triple that's an actual fibration. So that actually has the homotopy lifting property. So in terms of homotopy theory, you can consider each of these triples has an associated long exact homotopy group sequence. And you can pretend that this is a fibration so that you can study lifting problems to try to get into the fiber G mod H and things like this. And so that's essentially, that is essentially what's going on here. But in this case, since Z mod 2 is again a group, so in general this G mod H is just a space. Since Z mod 2 is again a group, you can actually extend one further to be Z mod 2. And so I'll mention the thing that I wanted to say over here, and then I'll say what is the relation to that. So this I want to try to wrap out. Relation between structure groups and classifying spaces. So let's say, suppose we have a bundle E to B with structure group G, and so we have an underlying principal bundle P sub G. So by our classifying theory, we know that we get some classifying map for P, going from B to BG. And E is isomorphic to pulling back EG and then replacing the G fibers with whatever F we had to begin with. Right? So suppose that we have this. Suppose rho from H to G is a group Hom. So,
Sorry, good question. This piece of G is from the fiber replacement lemma or something? What is this piece of G?
yeah, piece of G was like we start with an E. When we say it has structure group G, that means that like we chose this really nice atlas or transition functions in G, and then we're stitching the G trivializations back together with those.
Okay.
Yeah, so fiber replacement. Principal, underlying bundle, underlying G. So if we take a group homomorphism, then a reduction of the structure group to G, to H, along this row, is the same up to homotopy as a lift. So we have B going to BG, classifying our original bundle P. We have an H and a rho. And so a lift, a reduction of the structure group to H is the same as just lifting the classifying map to BH. So instead of fuddling around with these local trivialization garbage, we just have a space and a continuous function. We're asking, can we find a lift? And so the different lifts of the homotopy correspond to the different reductions of the structure group. So for example, if G is ON and H is SON, and this is just the normal inclusion map, the lift of this corresponds to an orientation. And actually, because this fiber is Z mod 2, this is telling you that at least on each connected component, there's only going to be 2 homotopy classes of lifts. There's only actually 2 orientations you can put on it. So now I'm going to do something really sneaky. How do I know if there is a lift? Well, the idea is if we turn this map into a fibration, you translate the problem into trying to take your map here and homotope it into one of the fibers. That can happen if and only if the composition to the base space is null homotopic. Right? So maybe it looks more sensible if I write it as a stack groups here. So that this is essentially a fiber of this fibration. And we have our B, was it B? B? Here's our classifying map. We want to know, can we lift? AKA, can we get into a fibration? Can we get into the fiber? If we compose with this map, by the homotopy lifting property, we get a lift into this, right? If we get a null homotopy downstairs, that means that this map gets the lift of that null homotopy, starts with this map and ends with a map that's in the fiber. So we see, like by homotopy lifting property, that you get a lift if and only if the composition to the space downstairs is null homotopic. Just saying this over and over again. Here's an interesting question: what is this map? Right? If we head back here, this quotient map is actually the determinant, right? So this map is B of the determinant. This space we wrote somewhere that I fucking erased it, right? This is the classifying space for O1. So these are line bundles. This gives you n-plane bundles. If you take your classifying space for an n-plane bundle and compose it with B det, you get a line bundle. It's called the determinant line bundle. That's why so that's tying it back to where we were. So this is saying that, you know, you get a lift if and only if the determinant line bundle is trivial. That's another way of seeing that result. Now I'm going to do some crazy stuff before I finish off. I said that this was a KZ mod 2-1, which means that this classifies cohomology with degree 1. So B det as a function from BON to a KZ1 is actually an element of the first cohomology group of BON with Z2 coefficients. And this has another name. It's called the first Stiefel-Whitney class. It's an element of cohomology. Your bundle is trivial if and only if its first Stiefel-Whitney class, your bundle's orientable. There is a lift to BSON if and only if the first Stiefel-Whitney class is 0. So that is a way of formulating this sort of obstruction class in terms of sort of just pure homotopy theory by using a lot of crazy associations that I didn't actually spell out anywhere. I would have if I had more time, but you never have enough time. Yeah, so that's definitely probably more than I should have said. So I will end my talk and open for questions. Thank you. Yes.
I have a stupid question. What is it?